Okay, welcome back. We're going to be talking today a little bit about modeling styles and what modeling styles represent. Modeling style is just a way to describe a circuit in VHDL. The idea is you're writing words to describe actual hardware that's being synthesized or generated by your synthesis tool. So there are three styles that are very, well, there are three styles in VHDL for generating modeling style. And one of them is called data flow. Data flow is something we've already seen in some of the examples we've looked at. For our initial VHDL code, we use data flow to describe the LED outputs for that circuit. Data flow is basically the idea of assigning a directly to a signal. You're assigning a value directly to a particular signal. Structural is the other methodology for specifying a style for a design, and that is a style that allows you to basically define a component and then plop that component into another design. So you're creating a component that actually can be reused over and over and over again. Structural is very powerful, and it's part of the reason VHDL is such a popular design language, because it gives you the chance to build something from scratch, test it, make sure it works perfectly well, and then reuse it over and over and over in your design. So good VHDL designers will create a library of components that they'll drop into their current design so they don't have to reinvent the wheel every time. And we use structural modeling for doing that. The last style that we use is called behavioral. And behavioral allows us to do a more complex description of our circuitry. So with behavioral, we can define things algorithmically, sort of like we would in a programming language. But we have to be very careful about using behavioral because it can be overused or excessively used. And a lot of times you find in industry it actually is overused. If you ever see a complex design defined with a single process inside an architecture, you know you've got someone who has not properly coded the VHDL. If it's a complex design, it should be broken into pieces, and then that does a lot of things. Number one, it makes the design simpler because the synthesis tool doesn't have to interpret things and try to figure out behind the scenes. It also makes the synthesis faster, significantly faster. And we're going to see techniques on how to do that in this course series. So let's start digging in and looking specifically at the individual styles themselves. So we're going to go and we're going to take a look at data flow modeling. Now, data flow modeling represents an assignment to a particular signal. And in the case of what we've seen so far, the Boolean expressions have been data flow statements. Very simply, you're assigning a value something based on Boolean logic, ands, ors, exclusive ors, that kind of thing. There's more to data flow than just basic Boolean, though. There are two very powerful data flow instructions. One's called selected signal assignment, and the other is called conditional signal assignment. And those are ways to define even more complex logic using data flow as a modeling method. And we'll see some examples of that. And that's really powerful, especially for combinational logic descriptions. The nice thing also about using data flow is it takes a lot of the work off the synthesis tool. In other words, the synthesis tool doesn't have to work as hard if you divide your design up and you use things like data flow statements, and it can create more optimal hardware for you if you do that. This is a block diagram showing the implementation of a data flow statement in an architecture. So notice that each individual statement, let's take the one in yellow here with the LED 1, corresponds to a box. The box has an output, and that's the signal that's being driven by the data flow statement, and then inputs, which represent the signals that are being used to make the decision. In this case, we can talk about things like switch 1, switch 2, and switch 3 being the inputs, and then LED 1 being the output. So back over here, we have switch 1, switch 2, and switch 3, the inputs, and LED 1 is the output. We have 3 statements. We have 3 boxes. Okay, so this is a simple way of diagramming in a block form the way the circuit's going to be laid out. Now, I love block diagrams because what that does is it helps reinforce the idea that you're not describing an algorithm here, you're describing a piece of hardware. You can use an algorithm for hardware, but we're really basically at the end of the day generating hardware inside our device, our FPGA or the CPLD device. So that's data flow. Let's take a look at the next style. And we've seen this again in our example, but we're going to talk about it a little bit more in detail here. And that is the structural modeling. Now, structural modeling is very, very powerful because it allows you to drop components that have already been created into your existing design. So you don't have to recreate them. So for this example, I've created 2 very silly components. You would never do this in real industry. And you certainly wouldn't need to be creating a 3-input OR gate or a 2-input AND gate as part of a component. But it's very helpful here for showing how structural modeling works and how you interconnect components using structural modeling. Let's start, instead of looking at the code really fully right now, I'm going to skip over to the block diagram that shows the code, basically that shows the blocks that are generated by the code and hardware. So notice that we're basically implementing the same circuit that we saw with our data flow statements, but we're doing it by pre-built components. We have 2 OR gate components that we're using here, and then we have 4 AND gate components that we're using here. Now, the OR gate component is just defined once. It's in a separate VHDL file and it's been predefined and you're dropping it into your design. And the AND has been defined just one time with a single VHDL file, and it's also being dropped into your file as a component. And you're replicating it in your design. You're using it multiple times. We're taking the same definition of the AND gate and using it 4 times here. And we're taking the same definition of the OR gate and we're using it 2 times here. See what we're saying? So we're basically able to take a design, duplicate it as many times as we need it using structural modeling. Now the interconnects are the difficult part. How do you connect up the inputs and the outputs to the various components? When we declare the components have various inputs. We have A, B, C as part of the component declaration, and X is the output of that component. When we drop it into our design, we have to connect these together. We have to connect switch 1 to A, switch 2 to B, and switch 3 to C. And we also have to connect X to LED 1. Now, how do we do that in words? Well, let's take a look at that. We're going to focus, since we just focused in on G1, let's take a look at how G1 is declared in here. So if we go over here, we can look here. These are the component declarations that are part of the architecture declaration section. And we're declaring that we have an OR component and it has the inputs as we just mentioned, A, B, and C, and it has an output of X, okay? And so if that's the case, A, B, and C, output of X, and then these are all standard logic and they have the proper modes set in here, in and out. We need to instantiate that component or create that component as part of our design. And to do that, we have to scroll down in our software. So I'm going to change my orientation here so we can scroll down nicely. And basically, if we look down a little ways, this G1, this is where we instantiate or create the component in our design. This part of the code does not create the component, it defines it. This is where the component is created in our design. And we can create multiple components. Like here is the G5 OR gate that we're also creating. All right, so now that we've got that under our belt, let's see how we do the connections. Now we saw before that the connections were made with switch 1 to A, switch 2 to B, switch 3 to C. And here we list switch 1, switch 2, and switch 3, and then the LED in here. Now this is called positional association. We list the inputs and outputs in order that they appear in the component definition. So if we look up here, you'll notice that A appears first, okay? And B is next. And C, and then C is next after that. And then of course X is connected to LED 1. So this is how they're connected. They're in positional order. They're in order from top to bottom and left to right here. So A, B, C, and D. So that's what positional association means. You're just basically putting them in the same order they are in the declaration. And we have another way of doing this, and it's called named association. We're going to see that later, but that's pretty much what's going on in this particular example. Okay, so that's how you declare things. Let's go take a look again at the hardware, and we'll see that we not only are declaring connections to the inputs and the outputs of the components by the way we put them in that argument list, we also have to connect them to other components, right? So you'll notice here, let me erase this. And you'll notice here that we have component G2 gets connected to component G5, and it gets connected via this wire, okay, or that interconnection. Now, how do we specify that in writing? How do we say that we're going to connect G2 to G5? And we have to do that, we have to declare a signal inside our design. Remember, these over here, these are ports in our entity. So those are declared in the entity, and those are ports. So those are named ports, and we can access those. But this is not declared in the entity. This is an internal signal. And so we have to create an internal signal as part of our design and then connect that internal signal to these components. So how do we do that? Well, first off, you create the internal signal like this by using a signal declaration, and this is in the declaration section of the architecture. And then we call it con1. So it's just a wire laying out there on the table, if you will. And then we have to connect it up. So you'll notice that in this declaration, let me switch pins here. You'll notice in this declaration right here, con1 is part of the list. It's the output of G2. So if we go down, con1 is the output of G2. So there it is. And then it connects to G5, the A input of G5, right? Or the first input. And so if we go down here to look at G5, we see that con1 is connected to the first argument, which is A. That's how we do the interconnection. So everything was handled in the structural by creating components and then creating connectors to connect those components together, and then declaring them as part of the argument list so that we know how they're connected. And so that creates this complicated little circuit here. Now, obviously, you would never solve this problem by doing this, but it does show a fairly complex way to implement structural modeling. You can do almost anything with structural modeling because any components that are declared outside can be dropped in, and it gives you incredible power. Your component then can be used in another person's. So it's a hierarchical thing. You can build and build and build until you have everything that you need. All right, so let's take a look at the last modeling style. Let me see here, switch over to the horizontal there, okay. And if we take a look at the last modeling style, it's called behavioral. Now, I'm about to introduce some things that you're probably not familiar with. Sorry, I need to turn on the lights. So you're probably not super familiar with because we haven't really discussed processes or behavioral modeling yet, but let's just kind of take a moment and we'll just stand back and we'll look at it and know that we're going to cover this in great detail in future courses, but I want to introduce you to the ideas that are part of behavioral modeling now, but we're going to hit it in full thing. So if you don't understand some of it, that's fine. This is just part of the, hey, here's the big picture. Look at what's going on here. Now, in our architecture, I am also showing you something new and different, and that is the declaration of constants. See, so we've got a few constants here to really help us in our code. You should never hard code anything in your design that's a numeric value. It should be set up in a constant, and then the constants are used later on in the code. So once you've done that, then you can get into the definition of your code. Now, what we're doing here is something that you would never really do in a real design. You'd never make your whole architecture one single process. But because this is a simple example, and we're just trying to show how to do things, it ends up being that way, right? So it's not a standard practice to make one process for the whole architecture, but we're doing it that way for simplification to make it easier to see what's going on. When we do behavioral modeling, we do so by declaring a process. So notice in the process declaration, we are declaring a set of inputs. That's what these are here. And we are declaring an internal variable called count. Now we'll get into more about how that works later, but it's just a variable that's local to the process and it only works inside the process, right? So other things can't see outside of it. Then the process is divided into two very easy steps. The first step is we're going to count the number of switches pressed. Now I know that because I put a comment there, and that makes it easier for people to look. We initialize the count to 0. We test the switch 1 to see if it's on, increment the count if it is, ignore it if it's not, and then do the same for each one of the other switches. So we're basically going through with our code and saying, hey, is this switch pressed? Oh, it is. Count goes up. If this switch is pressed, nope, I don't modify the count. So at the end, when we reach down here, we'll have an accurate count of the number of switches that are pressed, because that's the whole purpose of the algorithm, right? Now, once we have a count of that, the rest of the code, okay, the remaining part of the code is going to be updating that display, the LED bar display. And we do that using a case statement. And again, we're going to hit all of these things in great detail later, so don't panic if you're not familiar with it. But the case statement basically allows us to look at a single value and then use that value to determine what to do. So in this case, I'm looking at the count value. And if the count value is, for example, 1, then I'm going to turn the first LED on, and then the others will be off. And that's our bar with only one LED lit. Let's say the count is actually, in this case, 2. I would turn the first 2 LEDs on, and then the last one would remain off. So you kind of see the pattern here and how things are working. We're looking at a simple number, and we're using that number to determine what the LEDs are. And we're done. It's fairly simple. The when others clause here covers the case of when there are 3 switches. There is a very good reason for using others instead of using the number 3. And we will talk at length about that when we get into processes and such. But remember, the others keyword is incredibly important, and we'll be making use of that much later. Or not much later, but when we get into processes. So interestingly enough, we have a really clearly described algorithm that describes fairly complex hardware. I mean, it's not horrible, but it's very easy to see what's going on. We can see that we're counting the number of switches, and then we can see when we come down here that we're just updating the LEDs when the switches are activated. And one of the things that throws people is they'll look at this code with all those lines, okay, and they'll look at the other code that we wrote for data flow, right? So which do you think is more efficient? This code, or, and let's switch to the data flow code. And we're going to go switching back to the data flow code, that one. Now this is our data flow code. And so is this going to be more efficient hardware-wise? since it's only described in 3 lines of simple Boolean expressions? Or is this going to be more efficient? Sorry, I went too far. There we go. Or is this going to be more efficient? The truth is, and this is surprising to a lot of people until we talk a little bit later what's happening during synthesis, but this is actually no more inefficient than those 3 lines of Boolean. In fact, this code may likely be easier to maintain and more efficient than the other data flow code. The reason I say that is when we write Boolean expressions, we are telling it how to wire the hardware. We're not asking it to do any optimization. But when we write this behavioral description the way we've done it here, it could potentially go through an optimization process and find the best set of logic to generate the circuit if you haven't done a very careful job of doing your Boolean equations, really. It's up to human error at that point. The big takeaway is, no, it's not less efficient to do it this way. It doesn't really matter about how many lines of code you have, unlike in a programming environment with C and such, where it does matter how many lines of code you actually have. All right, so that's 3 modeling styles that we've talked about so far. Data flow, structural, behavioral. And do we have to pick one or the other? Is that a requirement in VHDL? And the answer is absolutely not. In fact, most good VHDL designs are going to be a mix of all of them, right? So you actually really do, when you're doing design work, you really are doing work where you're picking a mix of all of them. Oh, sorry, I forgot one thing. One more thing. This is a block diagram of our behavioral model. And one of the things, before we move on to the mixed stuff, one of the things I want to make sure you know is every single style can be drawn in the block diagram. And the key with behavioral modeling is the processes, each process declaration is a box in your design. So each process represents a box or a block with inputs and outputs. And so that's what we've drawn here. This is basically a block representation of our process called switch count. Now, how do I know it's called switch count? Well, if we look back here, we named it switch count. Let me erase this so we can see where we named it. Right there, that's where we named it switch count. So we called the process switch count, and therefore we can reference it in the block diagram with that same name. So this is the block diagram with the switch inputs, S1, S2, and S3, and then the LED outputs, LED1, LED2, and LED3. So it's a very simple block diagram for this particular thing. So a process is one block. Now, let's take a look at the mixed modeling, and that's a big deal. Now, in mixed modeling, we're mixing everything up. We're deciding to approach the problem in a slightly different way, and we're using a component. So in this example, we're going to use a component that was pre-declared somewhere else, and that component's job is going to be to count the number of inputs. That's its job. We're also going to introduce a new idea of grouping of signals called a standard logic vector, which allows you to group standard logic signals together in a bus. And so think about a data bus, like an 8-bit data bus that groups all the signals together that way. And so if we look here, we have declared 2 bus structures. And don't worry, we're going to hit this in great detail soon. But right now, I'm just showing you the big picture, remember. And so here, this is switch count, and it is a standard logic vector 1 down to 2. So basically, you're telling it the numbering of each bit in the bus, right? So it starts numbering from left to right. Left is 1, and then the next one's a 0. So bit 0 would be on the right, bit 1 would be on the left. This is a 2-bit bus. It can represent 4 possible values, which is very helpful if we're only counting whether or not 3 switches are active or not, right? So we can have a 0, 1, 2, or 3 as the output. The next one, LEDs, drives 3 LEDs. So we group that into one big group. It drives 3 LEDs, numbered 2 down to 0. And this is how you would declare that bus. Now, by doing it this way, by declaring it as a bus or a grouping of signals, we're able to create more meaningful constants and make our code a little more readable. So look up here, we've declared some constants that represent when the LEDs are on or active, right? Now this represents a bar display where it's an active low output, where 0 causes the LED to be turned on. And so you'll notice that the 3 LEDs are all zeros. That means all LEDs are turned on. And then 1 LED, well, you've got your lowest bit turned on. So that's why this is very helpful. You can create these nice constants in buses, and it makes it a lot easier to read. We've also declared our counter, our input counter. That's a separate component that we're bringing in from outside. So somebody's created a file called input counter, and they have created the component externally. They're bringing it into the design, and that's what this is all about. Okay, so this is an external component being brought into our design. Now we're ready for the main show, the main code. Okay, and to do that, we're going to look at this part of the code. And in this part of the code, you'll see that we have our component instantiation. This is where we have our input counter. We're calling it my counter. Remember, you have to give it a name. So all components that are dropped in structural have to have a name. We're port mapping it to signals in our design. And this is the input signals, and then there's the output signals. I know that because of the way the component is declared. There's the input signals, and then there's the output. Remember, this is positional association, so it's the order in which they appear inside the parentheses that determine that. I also have a process called LED driver, whose job is to look at the switch count value and determine what the LED should look like on the outputs. And that's all it does. And then I have some data flow statements that basically take the LEDs bus, and break it up into individual bits or in standard logic, and attach it to the LEDs 1, 2, and 3 signals. It's a lot easier to see in a block diagram. So if we look at our block diagram, you'll see there's our counter that takes 3 inputs and outputs a switch count of 2 bits. There's our LED driver. That's the process. Remember, that's the process we had in our system. It outputs 3 bits in a bus called LEDs. And then this represents the data flow statements. Now, remember I said data flow statements can be drawn as boxes. All data flow statements can be drawn as boxes. But if the data flow statements are simply taking a signal apart, taking a bus and breaking it off into pieces, we would use this bus tap representation. Each of these little things here is called a bus tap. It pulls off an individual bit, and then it attaches that to something over here. So this is really neat because it gives us a good insight into how the signals are connected. Bit 0 of the bus goes to LED 1. Bit 1 of the bus goes to LED 2, and bit 2 goes to LED 3. Now remember, we're going to look at these really close later. I'm only showing you this so you can see how this all works together. This is the mixed modeling idea, where you take the 3 modeling styles we talked about earlier, you use them in your design whenever they're the best fit, right? So you would use data flow when it works best, you would use structural when you're needing external components brought in, and process statements for defining more complex logic. So we're going to talk about when and how and what's best to use in our designs later when we get to our later videos. Thanks a lot for listening, and we'll see you in the next video.